So we would like to present the most general formulas that we will ever need in order to add explicitly points on an elliptic curve. Here I should say that we're following Silverman's book, and the reason for not going with an elliptic curve which has equation as simple as this is because in some cases we may want to represent the elliptic curve using a different equation that might make sense for different finite fields, or can have the best possible reduction for different finite fields. We're not going to explain what this means, but at this point, we're going to see later what it means. But for the moment being, let's just say that we would like to consider a more general form of an elliptic curve equation. Sometimes this is known as the Weierstrass equation. So it has more terms than the above equation, and it looks like this. So y squared plus a1 xy plus a3y, and this should be equal to x cubed plus a2x squared plus a4 x plus a6. And at this point, somebody might actually wonder if the indices that we use for these numbers have any particular meaning. I mean, somebody might say, why don't we just use A1, A2, A3, A4, A5? You can see that there's not even an A5, so we have A1 and A3 on the left, and then A2, A4, A6. And the idea is that, yes, there is a reason, and it has to do with the behavior of these terms when we apply a transformation, in particular the powers by which different parameters seem to change for these numbers. So that's exactly what the role of these indices is. But the truth is that we will not need to explicitly know this role, so we will leave it at that. So here we suppose that we have a point that has coordinates p naught equals x naught comma y naught. One thing that we can say is that this is not the point at infinity. As usual, the point at infinity will have coordinates or projective coordinates 0, 1, 0, and has to be considered separately. So this is a non-zero point. And we would like to give the formula for its opposite. And the formula for the opposite is going to simply be x naught comma minus y naught minus a1 x naught minus a3. So this represents the opposite of this point. And now we would like to give the formulas for the sum of 2 points. So imagine that we have P3 is equal to P1 plus P2. And imagine that these points are represented by x1, y1, x2, y2, and x3, y3. Now, there's certainly a case where the point that we're going to get is not a point that can be described using these coordinates. And for this, we can actually use the description that we just gave. So if we use 2 points that are opposite of each other, so in particular, for this to happen, we should have x1 is equal to x2, and y1 plus y2 plus a1 x2 plus a3 is equal to 0. So if this happens, which if you pay attention, it really follows this pattern, then from these two we will know that P1 plus P2 is simply the point at infinity. And the point at infinity is the neutral element of our group. Infinity. Let's spell things correctly. So we consider this to be a special case. And then if not, so if these two equations do not hold, then we have to define two numbers. Then we define lambda and mu. And this lambda and mu, I'm going to give the definition in 1 second. I'm going to show you how these numbers are going to give us the coordinates for x3 and y3. So in particular, x3 is going to be lambda squared plus a1 lambda minus a2 minus x1 minus x2. And y3 is going to be minus lambda plus a1 x3 minus mu minus a3. Of course, you can see that in the cases that we described, meaning when a1 and a3 are 0, these formulas get simplified significantly. So now to give the whole picture, so these are really the most generic formulas that we need here. So let's put them in a box. And in order to finish the whole story, we just need to define what lambda and mu are. And lambda and mu are defined in two different ways. So let's start with lambda. So lambda is given by just the slope between the 2 points. If this slope makes sense, if the denominator is non-zero, and is given by an expression that involves differentiation. So if you pay attention, what you get on the top is really the derivative of the polynomial on the right with respect to x. Minus this one term, a1 over y1, over 2y1 plus a1 x1 plus a3. And this is if x1 is equal to x2, which means we cannot define the lambda with the above formula. And how about mu? So mu again has a simple expression if x1 and x2 are different from each other. So we have y1 x2 minus y2 x1 over x2 minus x1. This is if x1 is different from x2. Otherwise, if x1 is equal to x2, then that will give us minus x1 cubed plus a4 x1 plus 2a6 minus a3 x1, I'm sorry, y1 over, and the denominator is the same as we had in the case of lambda when x1 was equal to x2. And this is if x1 is equal to x2. So lambda and nu are defined by these formulas. The generic formulas, again, are this one and this one, which are pretty simple. You won't usually have x1 is equal to x2. If you have them, then you have more special formulas. And this is the formula for the operation. Again, if a1 and a3 are equal to 0, this becomes much simpler. One can almost memorize these formulas in the most generic cases that we have, or in the cases that we have seen. Regardless, it should be more or less straightforward to implement those formulas in a computer program. We just need to make sure that whatever programming context we use, it can deal with rational numbers rather than making the numbers into decimals. And that's all. Thanks for watching.